everyone, today we will be diving into one of the most fundamental concepts in statistics and machine learning. Regression analysis, parameters, estimators and statistical inferences. Regression is the backbone of predictive modeling, whether you are analyzing stock price or predicting customers' behavior or even training AI models. Regression helps us to find relationship between variables and make accurate predictions. And here are the topics we will cover in this session. What is regression? Understanding the regression equation, how to estimate regression parameters using OLS method and statistical inferences, model performance and R-squared for how to measure accuracy, a quick hands-on Python demo, building a simple regression model. Let's begin. What is regression? At its core, regression is a way to find patterns in data. If we can understand how one variable affects another, we can make predictions. Okay. And if we plot house sizes in the X plot and prices in Y plot, and we can just randomly sizes. And I have plotted some random data in house sizes and prices. Now we can see the trend. Whenever the house sizes increases, like house sizes increases, then price of house is also increases. Now I have plotted a line which defines when house sizes increases and the prices also increases. The regression helps us to answer the question like, what is the price of house when house sizes is 4? So we can simply find now we can see when the house size is 4, the price of house is near to 15 million. Going through real-world examples of regression analysis, regression can be widely used in various sectors like finance, marketing, healthcare, and weather forecasting. For example, for finance, we can predict stock prices based on past trends. There are many types of regression, but today we will focus on the most common one, linear regression. Let's break it down step by step. The formula for linear regression is y equals to beta 0 plus beta 1 x1 plus error function. Y defines the dependent variables and x defines the independent variables, which means we have to find y in the base of x. And beta 0 means the intercept, and beta 1 means the slope, and e means the error term. Beta 0 determines the baseline value of y when all predictors are 0, and beta 1 slope determines how much y changes when x changes. If we try to plot data points, we try to fit a line that best represents the relationship. This is called linear line. Now that we understand the regression equation, how do we actually find beta 0 and beta 1, which means slope and intercept? We use a method called ordinary least square OLS. The formula for OLS is
beta equals to x power t into x power minus 1 into x power t into y. Beta indicates intercept or slope. X indicates matrix of independent variable predictors. Power t indicates transpose of x, and it is the inverse of x power t into x, and y indicates vectors of dependent variable actual outputs. When it is used, this equation is used in multiple linear regression where we have more than one independent independent variables. The OLS estimators finds the optimal beta values that minimize the sum of the square errors.
Now I'm starting a graph, and these are the data points, and this is the regression line. OLS finds the best fit line by minimizing difference between actual price and predicted price. It tries to make residuals or errors as much as small possible. If the residuals are large, our model is inaccurate. If our residual is small, our model fits well.
Example of good versus bad residuals. Differences between good residuals and bad residuals. As we can see in good residuals, there is small error between regression line and data points, and in bad residuals, there is a large error between regression line and data points. By this example, we can predict is this a good residuals or bad residuals.
One of the most common ways to evaluate a regression model is R-square method. For R-square method, the formula is R-square equals to for the R-square equals to 1 minus sigma y actual minus y predicted whole square upon sigma y actual minus y mean whole square.
And here is an example of bad versus good R-square. And R-square is close to 1 means the model explains most of the variance in the data. A low R-square means the model is weak. Let's build a Python model. While building a model, we have to import two things, that is a linear regression from sklearn and import NumPy as NP for training the data. Now, let's import linear regression from sklearn linear model. Import linear regression. Now we have to import NumPy as NP. Now let's run it, and it's already run, as you can see the tick. Now training data. In X variable, we are going to put sizes of house. Let's assume it NP dot array and size 1, 2, 3, 4, 5. And let's reset it -1 to 1. And in y-axis, we have to put the price of houses. P dot array and 1, 5, 10, 15, and 20. So let's run it. And it's already run, you can see the tick. So now it's time to train the model. Train the model. While training the model, we have to initialize the linear regression. So let's initialize our model. Model equals to linear regression, parenthesis. Now, we already initialized the model. We have to fit the model in X and Y. Model.fit X, Y. Now let's run it, and we can see the linear regression. It is already initialized. We are in the last part of our coding part. So at last, we have to do prediction. So we have to predict the output in the best of house sizes. So we already have house sizes in x-axis. So print. So it is for the prediction of for 6. Now comma. And to predict model dot predict 6. because we are predicting the size of 6. So now let's run it, and we can see the prediction for 6 is 24.6, which means the size of house of 6 is the price of 24.6 million. So by building this model, we can prediction the value of prices when the size is 6. So that's it for the building a model.
Today we explore regression, estimators, parameters, model evaluation, and even build a Python model. Can you think of real-world situation where regression is useful? Comment down below, and thank you for watching. See you again.